Right, good afternoon. Another session. Uh, I can see not a lot of people attending the session. No problems at all. This was not on the schedule, but it's just there so that we can finish up the course. And, and today we continue with sequential circuits. The last 3 sessions, I introduced what we call sequential circuits. And we compared them with combinational circuits. The main difference between them being one uses present inputs, one uses present and past, present and past, sequential circuits. We dealt this way in the last 2 sessions. We introduced a memory element. We introduced a memory element for sequential circuits. And we said the memory element is responsible for the feedback which gives the past inputs. And we said in sequential circuits, this memory element is called a flip-flop or a latch. A flip-flop or a latch. I gave a simple example of a memory element which is made of 2 gates. And I said, if I want to store bit 1, this is how I can store bit 1. This becomes my memory element. If I input 1 here, what it becomes with the NOT gate is a 0 here and another 1 here. And with a circuit like this, it means I have stored the information bit 1. This is how you store information. This is an example of a memory element. We talked of characteristics of sequential circuits. We introduced synchronous and asynchronous circuits. Synchronous, and asynchronous circuits. Synchronous and asynchronous sequential circuits. And we said synchronous, it involves the clock. There is timing. Asynchronous, the change in the states is due to the change in the inputs. For synchronous, the change in the state is due to the change in the clock. Yesterday, a lady came here and she complained about my handwriting in a very good way. And I asked them, there are a lot of lecturers who dictate notes. I am better than those lecturers. Right now, I am dictating, but at the same time, I'm writing something. I'm putting an effort writing something on the screen. So my handwriting is not the problem. If my handwriting is a problem for you, assume that I'm dictating notes. I just thought of it today. And I think it's a very good excuse for my bad handwriting. Right. Synchronous, asynchronous. We also talked of introduction of triggering methods with the clock. With the clock comes triggering methods. Triggering methods, we have edge and we have level. Triggering methods, we have edge. Triggering, we have level triggering. A typical clock, 1010101010. This is a typical clock. As it goes up, this is positive edge triggering. As it goes down, this is negative edge triggering. As it goes up, this is high. Yes, this is high level triggering. As it goes down, this is low level triggering. So in a sequential circuit, if I'm using the clock and I know that the clock is positive triggered, it means every transition from 0 to 1 every transition from 0 to 1, every transition from 0 to 1, there is supposed to be a change in state. Here, nothing happens. Here, nothing happens. Here, nothing happens. Positive change in state. If I'm using a negatively triggered, edge-triggered circuit, then when it moves from 1 to 0, there is a change in state. You understand this, everything that follows with triggering your home end drive. Right, we introduced the SRLH. We introduced the SRLH. We introduced the SRLH. And it says typically we have the one which is made of nons. And we say this one is called a low, active low SRLH. Why active low? Because what is the input in these two? So here we have Q bar. So here we have Q. I think it looks something like this. Here we have Q bar. So it comes here. It comes here. And it comes here. Right, I think that is an SRLH. Why is it called an active low? Because the input here going in this last NAND gate, this one and this one, the inputs are lows, zeros. So we have S here, we have R here. They are lows, and outside we have S and R. We have a NOR. This is active high. Why is it called an active high? Because the inputs going into the last OR gate, or the inputs which are directly linked to the output, are high. So we have Q bar, NOR, we have Q. Output here, output here. You're supposed to know these things. Right. Here, the input is high, and it gives you direct output. Here, the input which gives an input here is S bar. It is low. That's why it's called an active low. And this one is called an active high. All right. However, both these two, they give you the same truth table. These two, they give you the same truth table. This is the truth table for an SRLH 0011 0011. The truth table for the SRLH, it has 3 states, or let me say 4. We have the memory state, which is 00. We have, please do excuse me, Zoom recording. All right, so we continue from where we left off. I was saying 00, this is our memory state. 01 is state tip.
It's reset.
01, we have the reset state. Then we have the set and
Set, then illegal.
For begin.
right. So the memory state, this is Q plus next state. This is the present state. When I say Q plus, this is the next state, which means Q is equals the present state. Present state. So here the present state is equal to the next state. Here we have reset 0, 1, illegal. This is the truth table for the SRLH. We discussed this. Then we discussed operation of how we came up with this truth table using a NOR gate. I think we did that. We also talked of the, so this is the block diagram. S, R, oh yeah. So we have S, R, then our output Q and Q bar. Block diagram. This is what an SRLH will look like. 2 inputs, two outputs, Q and Q bar. The truth table doesn't change, even if it's active low or even if it's active high, the truth table remains the same. With the truth table, we saw that we also have the characteristics table. The characteristics table shows you how to find the next state. How do you find the next state? So for the characteristics table, now you have the input, the present, you have the inputs, which changes states, S and R, then you have your next state. So if I have 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, what will be my next state? Right. List Rewano really list Rewano says chat participants. Right, unmute yourselves. Unmute. Right, unmute yourselves. Right, I need you here. Memory Tagadi. What is the next state for the first row? What is the next state for the first row? This one. What is the next state? Memory Tagadi.
Honestly, I'm not sure.
No, give me an answer. I need an answer. Wild guess?
Memory state.
0.
Yeah. Ana memory aru besera umogo. Beware. Memory Tagadi. Here, our next state is 0. How did we get 0 memory Tagadi? We got 0 because we are using this table right here. What this table tells us is if S is equals to 0, R is equals to 0, we have what we call the memory state. When we have the memory state, it means the present is equal to the next.
1.
So memory Tagadi, another case, we have those inputs. What will be the next state here?
1.
What will be the next state?
I think it's 1.
Don't think it is 1.
Okay, say.
It is 1 because this state is supposed to be equal to this state because we have 0, 0 here. 0, 0 means we have the memory state. Memory Tagadi, what is the next state for this row? Row number 2.
That's 1.
It's 0.
It's 0 memory Tagadi. Why? Because S is equals to 0, R is equals to 1. When S is equals to 0, R is equals to 1, we have what we call what memory Tagadi? What is this?
Reset.
It's called the reset state. For the reset state, whatever the present state is, you get a 0. That's why we have a 0 here. Memory Tagadi, third row. What will be our output in the next state?
1.
Why?
Because our S is 1.
Because our S is 1 and we have the S, we have the set state. For the set state, the output will always be equal to 1, whatever the input. And lastly, memory Tagadi, what will be the output here?
1.
The output is illegal. We don't have an output because we have 1, 1 here, we have 1, 1 here, we have illegal here.
Okay.
Right, so we gave another example, 100, 001, 000, and we wanted to find the outputs. Here we have the memory state, another memory state, reset, reset. And provided in the exam, you have Q, S, R, and you want to find Q plus. What you need to know is the truth table of your sequential circuit, of your memory element. let me say, you need to know the truth table of your memory element. And if you understand the truth table of your memory element, then you can come up with the characteristics table. For whatever input you have, you can come up with the corresponding next state, provided you know how these change. 00 memory, 01 reset, 10 set, 11. We don't have this one. We discussed the SR latch. We also discussed the SR flip-flop, RS flip-flop. And we said, basically, this is a latch plus a clock. It functions almost the same way as a latch, but now a latch on its own, this is asynchronous. The change of states, asynchronous, yes, forget asynchronous pop-up. The change of state is determined by the change in the inputs only. But for an RS flip-flop, the change of state is determined by the clock. Therefore, we have an asynchronous, nope, asynchronous, synchronous, sequential circuit. That's the difference between the latch and the flip-flop. A latch has no clock. A flip-flop has a clock. A latch is asynchronous. A flip-flop is synchronous. All right, we introduced the RS flip-flop and we gave the truth table. So the RS flip-flop block diagram, we have, let me say 3 inputs, S, R, then we have our clock, CLK, we have our outputs, Q, and Q bar. This is what it looks like. The difference with the latch being here with the clock. But for the truth tables, you could see they're almost the same. The difference is we now have a clock. So now for inputs, we have a clock, we have S, we have R, we have next state. So when the clock is 0, whatever the inputs, we have a memory state. When the clock is 0, whatever the inputs of S and R, we have the memory state. However, when the clock is 1, the RS flip-flop behaves like the RS latch. 0, 1, 0, 1, 0, 0, 1, 1. When clock is equals to 1, latch is equals to flip-flop. Same everything. CLK is equals to 1. So here for 0, 0, this is Q memory. This is 0, reset. This is 1, set, then illegal. These two are almost the same. Difference is this clock. Right, for the state transition table, for the characteristics table, same things. You have the inputs S, R, and your present state. You have your next state, 0, 0, memory. If I have a 1 here, it means I have a 1 here. 0, 1, this is the reset. If I have a reset state, whatever the input is 0, etc., etc. Very simple stuff. We continue with what we call the excitation table. Right. So for the RS flip-flop, RS flip-flop, we have the truth table. For the truth table, we have clock, S, R, next Q. We have 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 1. When the clock is 0, we have the memory state. So our next state here is Q, 0, 1, illegal. This is our truth table. We can go on to find The characteristic table. The characteristic table will show you what the next state will be. How do you find the next state? You have the present state, you have your input, then you have your next state. So I have 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. 5 minutes, 0, 0, 0, 0, 1, 1, 1, 1. Right. What will be my next state here? Participation. Be quick, please. Anybody?
0.
0.
0.
And they don't.
1.
0.
0.
1. Illegal.
Illegal.
Legal.
1.
1.
0.
0.
1. Illegal.
Right.
Illegal.
These are our next states. With the characteristics table, we can find what we call the excitation table. Using the characteristics table, we have what we call the excitation table. How do we come up with the excitation table? We have our current state, we have our next state, and we have our inputs like this. The excitation table shows you if, watch, if I want to go from 0 to 0, what should be my S and R? That is why we have the excitation table. If I want to go from 0 to 1, then what should be my SR? If I want to go from 1 to 0, what will be my SR? Now, if I want to go from 0 to 0, I go back to my characteristic table. Here, I have 0 going back to 0. What is my SR? My SR is 0, 0. Someone confirm that.
Confirmed.
Thank you very much. Here I have another 0 going to 0. What is my SR? 0, 1. Do we have another 0 to 0 there? Nope, we don't. Using this, I can then go on and fill here. I know if I want to go from 0 to 0, my S is obviously a 0. But what is my R? My R is whatever the variable is. If my R is 0, then I'll go from 0 to 0. If my R is 1, then I'll go from 0 to 0. This is where we bring in I don't care. When we did our Kano map, we mentioned there are values which we call I don't care. This is where they come in there. So we don't care what is the value of R here. We get 0, 0, whatever the case. We go to 0, 1. Here I have 0. Let me put red. This is 0, 1 here. This is 0. This is the only one. If I want to go from 0 to 1, what will be my SR?
1, 0.
1, 0. If I want to go from 1 to 0, this is my 1 to 0. My SR will be 0, 1.
0, 1.
If I want to go from 1 to 1, here, let me change.
1.
So I have this one. I have 0, 0. I also have this one here. 1, 0. It means I have I don't care and 0. Someone say amen, Banis, and that up.
Amen.
Thank you very much.
Amen.
Amen.
1 year is enough. Everyone move on or take them. Yeah, men say above 10 points. Move on or reason as a fan. One I understand, everyone understands. This is how we come up with the excitation table. Now I know if 1 minute, if I'm building up my circuit, and I want my state to go from 0 to 1, what will I do? I'll come to the excitation table. I change my inputs to 1, 0. If I change my S and R to 1, 0, it means my states will go from 0 to 1. So I'm trying to build up a circuit. I want to go from 1 to 0. How do I go from 1 to 0? I change my S and R to 0 and 1. We'll discuss later how do you change your S and R to be 0 and 1, or to be 1 and 0, or to be 0 and 0. Join me in the next session.